our own Simon Hamner is going to give us some real eye candy on the Lunar Reconnaissance Orbiter. So, Simon, take it away.
Okay. You know, as amateur astronomers, we tend to have a bit of a schizophrenic relationship with our nearest celestial neighbor, our own moon. Some among us even consider the moon to be a source of light pollution that degrades our views of faint deep sky galaxies and nebulae. But there are others who like to observe the moon's surface, following the passage of the shadows that emphasize the definition of many of its most interesting features, ranging from impact craters to valleys and to cliffs. But we tend to treat the moon as a collection of curios, or worse, as a catalogue. A collection of stuff to be observed and checked off on a list of items whose origins we may not really understand, no matter how much we go back and look at these things. Next one, please. There are many publications available to guide us on our exploration of the moon. Personally, I started with Ernest Cherrington's Exploring the Moon, which was first published in 1969. I was a little late in discovering Antonin Ruckel's Atlas of the Moon in its 2004 updated version. It's a magnificent roadmap to all things lunar, but that's all it is. It'll guide you geographically, but it doesn't explain what it is you're looking at. Even the RASC's Williamson Lunar Observing Program, despite its geological introduction, which I had a hand in editing, it still takes a find, observe, name, catalogue-style approach to the moon. I think that the best moon books available today are still planetary geologist Chuck Wood's The Modern Moon, published in 2003, and the Kaguya Lunar Atlas that he co-authored in 2011, and I have a copy of that one here with me if anybody wants to see it during the break. Now, these books are not so much atlases. They're more of an investigation of what's been going on with the lunar surface for the past 4.5 billion years, with an emphasis on interpretation and understanding of process. And by process, I mean geological process. So when the RASC National Discussion Group was recently all a Twitter with news of Chuck Wood's latest offering entitled 21st Century Atlas of the Moon, I sent in my order. Now, for me, the most attractive aspect about this new atlas was that it was announced to be based on the spectacularly high-resolution imagery that NASA's Lunar Reconnaissance Orbiter is still sending back from the moon on a daily basis. And when I say spectacularly high resolution, I mean it. The best resolution images they're sending back are 0.4 meters per pixel. Wow. I was disappointed. Now, don't get me wrong, this is indeed an excellent atlas of lunar features for amateur astronomers, so they can seek out features from their backyards. However, the Lunar Reconnaissance Orbiter photographs are the ones that are used as the broad-scale locator images for navigation, while the detailed images to guide observation are mostly taken from older missions with lower resolution than those that the Lunar Reconnaissance Orbiter camera is capable of. So I asked myself, what do I expect of a truly 21st century atlas of the moon? When I discussed this with the fellow members of the Ottawa Valley Astronomers and Observers Group, the OAOG, at their last February meeting, the 30 to 50-year-olds, remember that, 30 to 50-year-olds immediately pulled out their iPads and went online to investigate the LRO images that I was discussing with them. That's exactly what a teenager or a 20-something would do as well. So I think that a 21st century atlas is really something that utilizes all the tools available to amateur astronomers today in order to help them better understand what they're observing through their own backyard telescopes. Let me put this philosophy into a tangible perspective. If I were to ask you, what do you imagine the lunar surface looks like if you were actually standing on it? And most would probably reply, pretty dusty. And if I asked you, what do you imagine the interior of a small impact crater looks like if you were actually standing in it? I think most of you would reply, pretty smooth. And if I was to ask you, what do you imagine the central peak of a complex impact crater looks like if you were actually standing next to it? And I think most would reply, a mountain of solid rock. The detailed LRO images, LRO, Lunar Reconnaissance Orbiter images, publicly available on the web would show us that even if we can't see that sort of detail that the LRO can through our own telescopes, our perception of what we think we're seeing through our own telescopes is commonly wide of the mark. So what I'm going to do here is I'm going to run a selection, just a selection of detailed, very high-resolution lunar reconnaissance orbiter images by you to give you a taste of what they can show you and how they will positively impact on your own lunar observing experience and understanding of what it is you're actually looking at. Now, each slide will have a lunar location inset in the top right corner to help you place where we're looking. So let's start with impact craters. Next one, please, Chris. Now, here's the central peak in Aristarchus crater. There's the central peak right down there. And it is indeed made of solid rock. In fact, you can clearly see that it's made of compositional layers. See the dark layer, white layer, grey layer here? Made of compositional layering in the peak, as well as in the terraced wall in the background. Look at the layering here. See that dark layer there? And then a white layer there, and then more white over here. So we're clearly looking at solid rock there. Next one, please, Chris. But here is part of the central peak on Tycho crater. And it looks pretty rubbly. Note the scale bar up here. That's 200 meters. Notice also the 130-meter long boulder that's sitting on top of the peak at this location. We're at 2 kilometers above the crater floor here. Next one, please. Well, here's the summit of the central peak of Bullialdus crater, and this is just a pile of rubbly boulders. This isn't the whole peak, this is just the highest point on it. But what's this smooth stuff here that's surrounding it, and in fact even seems to be on some of the bouldery material? Is it really dust? Next one, please. Well, here's a clue on the floor of a small crater known as Linné F. Again, note the scale bar, that's 200 meters. And you've got a central mound here in the floor of the crater. And it's surrounded by a smooth moat of impact melt. That's this medium grey material here. This stuff out here is the base of the crater wall. And that impact melt is a continuous sheet of molten rock that was generated by the heat of the impact that formed the crater, and melt which then fell back into the crater cavity and pooled on the crater floor. You might notice these house-sized boulders around the edge here of the impact melt pool. Next one, please. Now, how do NASA scientists know that this smooth stuff is, in fact, impact melt and not dust? Well, here's a sheet of the smooth stuff on the lip of the crater Olcott. And this is on the far side of the moon. Note my convention for far side of the moon. You can see the near side with a cross on it. Now, the crater itself is to the top, and this is the external shoulder, if you will. And notice these lobes and this smooth, dark material here. In fact, that lobe there has even broken as material started to try to slide down the slope. But look at this tongue down here. I'm afraid it's in the lower part of the image. I can't do much about that. But that clearly has flowed. That is melt. Next one, please. Now, here's a sheet of impact melt, this smooth grey material here. It's on the floor of Thales crater at the base of the crater wall. The crater wall is back here, and this is the crater floor. Now, notice the house-sized boulders, these ones over here. And some of these are even quite large too. There should be a scale bar on this one. No, I forgot to put one on this one. They are house-sized, sort of 30 feet across. And notice how they're absent as you come even closer to the floor of the crater. Notice also these squiggly channels here. They're all over the place. These squiggly channels, all of which seem to be pointing down towards the floor of the crater. And they're running over the surface of the smooth impact melt. We'll come back to the boulders in a minute, but meanwhile, let's look at channeled impact melt on the moon. Next one, please. Now, here are branching fingers. Down is this way. This is upslope, that's downslope. These are branching fingers of impact melt, which are flowing over a bouldery surface. These are the boulders, you can see them very clearly. There's the scale bar, so these again are house size at least. And this is on a surface adjacent to a Grotrian crater. Again, note the scale bar. This is a very detailed image. Next one, please, Chris. And at the same scale as the previous image, this is a single-channeled flow of impact melt near crater Ingelis. Here's the channel of melt. But notice the details. The flow is flanked. You can particularly see it well on the southern side here, but it comes around that side as well, but it's really nicely shown here. It's flanked by boulders up to 10 meters and more. which the flowing melt, which was flowing this way, has actually shoved to one side. And if you look at the termination, you can see that there are multiple lobes. There's a lobe there, there's another lobe there, and another lobe there. So this impact melt was not just flowing, it was flowing in pulses which actually pushed through the older terminations of the earlier pulses of flow. And we're talking about stuff occurring in space of minutes here. Next one, please. This is a little dark, but it's good enough. This is an example of channeled impact melt flow from Lowell crater, and it nicely illustrates this concept of a second pulse of melt flow. You can see there's the original flow, and then here is a new lobe forming, either because the impact melt was breaking through the old flow, or maybe it flowed over the top of the old flow and then formed a new termination. Next one, please, Chris. Now, not all that flows on the moon is necessarily melt. At the same scale as the previous images, there's 100 meters scale bar. This is granular flow of sandy to gravelly debris running across the side of Pytheas crater, where we can also see layering here. That's down, by the way, downslope, upslope, and you can see layers here, which are actually the layers of the individual basalts which went to fill the mare. More on the basalts later. But remember, this is dry flow. There's the source of the flow. Here's the gravelly material which flowed and cut a channel through these layers of basalt. And then when it got down to the crater floor, the material slowed down and it formed a fan, a debris fan. But remember, this is dry. There's no water involved here. Next one, please, Chris. Within the small crater Clavius E, which occurs within the larger crater Clavius we know so well, we see this remarkable example of fine-grained debris that has flowed in a channel over the top of older bouldery debris. Here's the bouldery debris. You see it looks so pimply, but in fact it's in relief. And more bouldery debris here. And you see these fingers at the end of the fine debris flow. There's the debris flow itself. It's got very few impact craters in. There are a few. And these are very young, and NASA is asking itself seriously whether these debris flows are forming today. I'll admit that this one's not easy to distinguish from impact flow. Next one, please. Here on the walls of Gardner crater, these walls are plastered by multiple braided fine debris flows. The smooth material in the medium grey, you can see it here. You can see them all through here. These are braided fine-grained debris flows that appear to cover older, coarser-grained debris flows. You can see the coarse grain here, and you can see it looks granular up there. Those are boulders. There's 100 meters. So you've essentially, from the same impact, you've got boulder debris flow being ejected from the crater, and you've got this fine-grained debris flow as well. Next one, please. And this is a glorious example from Freres crater where very narrow, fine-grained debris flows, that's upslope here, downslope here, there's the crater floor. There are literally, every one of these streaks is a fine-grained debris flow. There are hundreds of them. And they're draped over a boulder apron, as you can see here in the lower slopes of the crater wall. That's just a carpet of boulders, somewhere in the 10 to 20 meter size. And then down on the floor of the crater, you can see even coarser boulders again. Which brings us to look at lunar boulders in general. Next one, please, Chris. Now this is right down here. This house-sized boulder has bounced its way all the way down the central peak of Schiller crater. You can tell it's bounced because it's actually jumped from pit to pit to pit to pit to pit. I don't need to say anything more about that. Let's move to the next one. And these curved trails here, you can see them there, and then there's two here, and there's another one over there. These are down the wall of Picknell crater on the far side of the moon. These clearly rolled without bouncing. See, they're continuous trails. Next one, please. And this one I like. This 10-meter plus bouncer here rolled all the way down slope, and then it did a hole-in-one in a pre-existing hole. Notice the scale bar up here. This is pretty good stuff, you know. I mean, look at the detail on these house-sized boulders, which are confined to the base of the slope. The reason this one rolled so far is that without any air, the thing that determines how far and how fast something will roll, is essentially a matter of its kinetic energy, which is a function of its mass, which is a function of its size. So the big boulders actually roll further than the small ones. Next one, please. Boulders are everywhere on the moon. Remember my question about what the interior of small craters look like? Well, this one near Rhina Gamma has a central pond of impact melt. There it is, right down there. There's the exterior of the crater, okay? That's the crater wall. And it is absolutely blanketed inside the crater with boulders that fell back from its impact ejector. I don't think if you were looking at that through your telescope, you'd expect to see something with a bouldery carpet quite like that. Next one, please. And this one I really like. Personally, I'd always simply assumed that ejector rays, you know, the bright streaks that we see radiating from impact craters like Tycho, I'd always assumed they were made of dust, until I saw this image of an ejector ray from a crater within the Mare Moscoviense on the lunar far side. Look, there's the scale bar. These boulders are going from 50 meters to 10 meters, and that is the proximal end of this ejector ray. What did you think they were made of before I showed you this picture? Okay, let's turn to lunar volcanism, starting with the Mare basalts that fill the up to 1,000 kilometer across multi-ring impact basins that we can see on the lunar near side and we're so attracted to. Next one, please, Chris. So here we're looking at the wall of Bessel crater, and we see these fine layers. You can see them here. And there's the scale bar, about 100 meters. And each one of these represents an individual basalt lava that contributed to filling the Mare Serenitatis in this case. Each flow is probably about 20 meters thick. And the cavity, the original cavity of the Serenitatis basin was likely about 10 kilometers deep. That's a lot of individual lava flows. Next one, please. I like this one. And here's the lunar equivalent of the Highway 174 nightmare. A 50-meter wide collapsed pit in the basalt flows of the Mare Tranquilitatis. The way it formed was the lava was still flowing underneath the frozen skin of the lavas here and left a bit of a cavity underneath and things collapsed, just like Highway 174. But look carefully, and what can you see in the illuminated part of the floor of that cavity? Boulders. This is high resolution. Next one, please, Chris. Okay, here's a favorite of many lunar observers, Hyginus crater and its valley segments. Again, note the scale bar here, we're up at 10 kilometers. Obviously, this image is not 0.5 meters per pixel. The crater itself, there, is not an impact feature. We know it's a hole in the Mare basalts without a raised rim. And in fact, it's a volcanic caldera, which means it's a collapsed volcanic vent. That's nice, but the thing I like about this picture is notice these pits all the way through this valley segment up here to the upper left. These features are related to exactly the same volcanism. And with a good telescope, you can actually make them out. Next one, please, Chris. So now let's look inside Hyginus crater at its floor. Note the dramatic change in scale here. We're now at 200 meters. And these bright things here, and this is just the biggest of the bright ones. And these are actually collapsed pits in the floor of the collapsed caldera. If you like, they're proof of the volcanic origin of Hyginus crater. This is quite remarkable. Next one, please. So by now, we're all aware that squiggly valleys are the erosional products of rivers of flowing volcanic basaltic lava on the lunar surface. And you can see them here coming across beautifully like this. They even continue up through here. There are more up through there too. However, until Lunar Reconnaissance Orbiter, I had absolutely no idea of the existence of these exceptional examples in the vicinity of the small crater Herygonius K. And this is Herygonius K. And for scale, it's about 10 kilometers across. Next one, please. Here's another favorite of lunar observers, Posidonius crater. But did you know that one of the most prominent fractures in inverted commas in the crater floor is in fact a 130 kilometer long squiggly valley carved by basaltic lava? And here it is. I say starts. It may end here. I really don't know which way things were flowing. But it's a squiggly valley which comes up like this, and then it actually hugs the floor, the foot of the crater wall. And next one, please, Chris. And finally, a perennial favorite of us all, Schroeder's Valley, just north of the Aristarchus crater on the Aristarchus Plateau. So what, I hear you say? Been there, seen that. But did you know that there's a squiggly valley running all the way down, and there it is again. I can just see it there, and I think I can just see it there, and I think I can just see it there, and I think I can just see it there, running all the way down Schroeder's Valley. And when you get to the end, Schroeder's Valley, look, it turns and goes this way. And this squiggly thing keeps on coming. It cuts across it down to there. Clearly, the squiggly valley represents a younger event. Next one, please, Chris. Now, I introduced this presentation at the beginning as a taster to what the Lunar Reconnaissance Orbiter has to offer us as amateur astronomers through our own backyard instruments. Let me end by suggesting that the Lunar Reconnaissance Orbiter has in fact provided us and continues to provide us. They actually have new images going up every couple of days on their site. A truly 21st century lunar atlas that already can teach us how to better understand our nearest celestial neighbor. To help you find your way through the growing Lunar Reconnaissance Orbiter image archive, I've downloaded about 85 detailed images that I've briefly annotated with commentary, and I've also included the URL for each image, all of which Chuck O'Dale has now actually posted up on the RASC Ottawa Centre website on the articles page under my name. This will allow you to immediately jump into the Lunar Reconnaissance archives, actually going to looking for images where you'll find on the pages which I'm guiding you to, you'll find excellent location images and explanatory notes, short explanatory notes, which are well written for the non-expert. I'm not often very complimentary about NASA, as many of you know, but in this case, they really have got it right. So I would strongly encourage you to peruse the actual Lunar Reconnaissance Orbiter resource itself. It will literally change the way you observe and think about what you see on the moon's surface through your own telescopes. Thanks for listening.